We're going to model something more complicated for this final project, well, we can start analyzing this feature, this Revit feature of the solar analysis with this box. I think it's very useful. Okay, so I will start doing different things, and we have to do this with an actual building, with an actual project. This is just the box, and but I think the analysis is the same. We have to go to the Analyze tab, and we have to run the solar analysis. I would like to duplicate this, duplicate view, and let's rename this to solar analysis. Sometimes Revit collapses when you are creating a lot of solar analysis, and then you change something, you run another solar analysis, and you change something else, and you run a third solar analysis. So at the end, Revit collapses. So I recommend you first, having different 3D views for different solar analysis. That's a good option. And second, save it on a regular basis. Because if you are working with Revit for 2 hours, running different solar analysis, it can end up collapsing. And it's annoying, especially if you are. So I have created a new one, a new 3D view with a solar analysis. And well, this is quite simple. You click here. Well, first, I think first we have to work with the sun settings. Okay, so if we click here, sun settings, we can have a multi-day. By default, we have a year analysis from January the 1st until December the 31st in 2010. I mean, changing the year, yeah, the climate is changing, but over the last 10 years, it hasn't been, it should be the same. Anyway, if you want to try other year, you can select here the year you want. Then we have to select the location. Okay, now location matters. Well, location matters when we are running a thermal analysis, but it's even more relevant when we are working with the solar analysis. In Boston, Massachusetts, it's not, it shouldn't be enough. If you click here, location, if you know the specific coordinates of your, of the place you are working with, that would be more accurate. Okay, Boston, okay, it can, because it depends on where we are. So there are different weather stations. So we need to select a weather station that is close to our site. Anyway, we will change the location later. Today we're going to work with Boston. We will start with these sun settings, a year, but we need to know what we are doing. We are analyzing a year. And I always click this, sunrise to sunset. Because if we want to run the solar analysis, we want to analyze this when we have sun. So there is no point on analyzing this from midnight until midnight the following day. So I always click this, the sunrise to sunset, because I think it makes more sense. Okay. So we have selected multi-day, a year, and sunrise to sunset. This is a good way to start, then apply changes. And now we can run the solar analysis. First, set the sun settings. And then, because when we are aware of the sun settings, we know what we are doing. Okay, we're analyzing this throughout the year, and from sunrise to sunset. So the solar, and here we have this, and with this we have the custom. We have the custom and the annual PV. We will use this later, the annual PV analysis, but then we have to place PV panels. So far, we are just analyzing the amount of sun that we have on different surfaces. Custom, by default, you have all exterior roof exterior surfaces. Since we have only one building, that's fine. But we can always select the user selection. So we select the user selection. We always have this message, and we can click here. You see that by default, we have a plus. We click here, we are selecting a new surface, and then there is a minus. If we click here, we are not selecting this. Okay, so let's select the roof, this horizontal roof, and don't forget to click finish when you are selecting different surfaces or different areas. Finish. And now we have to click here. We can change the units to BTU per feet square. Here we have to use cumulative insulation. I'll explain what this is, but let's start with the cumulative insulation. And for the solar analysis default, yes, so you have a lot of options here. Just select this default. And you can even export this to a CSV file. We will do that later, and we'll see what we get here. Yeah.
What is a CSV file? Like, can it be right in Excel, or is it an ARCH?
Yeah, no, it's for the Excel file. So we can turn this into an Excel file, and it will be useful. Okay, well, we're going to do this. We're going to run the analysis, and then we will see the results in Excel. Okay. So this is useful for scientific articles. If you are working as an architect, architects usually we don't have this Excel file with all the data, the time. But if you are writing a report, maybe you might need this. But anyway, we're just analyzing the Revit. So click update. And this is it. This is the first analysis. What is the important information here? Well, the BTU. This is the total energy that we are receiving on this roof. Okay, so if we add up all the solar irradiance that we are receiving on this horizontal roof, at the end of this year, we have these 726 million BTUs. Another relevant information is the BTU per feet square. Okay, so we have BTU per square feet. This is relevant because the amount of total BTUs, the bigger the building, the more BTUs. But the effectiveness of the system, it's measured by BTU per feet square. Okay, so the more the BTU per feet square, the better. And here we have information about the project location, the start and end time, and we are running the cumulative installation. Okay, and as always, we have to compare. Is this good? 726 million BTUs. It sounds a lot, but is it the best option? Well, we don't know. So we can always save this. Well, take a picture. And I'm going to create a PowerPoint with different options, and then we will compare. This is our first option. Great. Okay, now I want to compare this to a tilted roof. I would make the changes in this file, not in the solar analysis file, because the likelihood of a collapse is higher in the solar analysis 3D view. So here I'm going to edit the footprint, and I'm going to define slope here, and this is too steep. Let's say 3/12. Okay. So let's compare this to the previous option. So now we go back to the 3D solar analysis. And I want to Make sure that we have exactly the same settings, because if we change, we can't compare anything. So it's custom, user selection. So I'm selecting this roof. I finish. And then this is the cumulative insulation with the right units, the default SOAR analysis. So let's update. Okay. So what do we find here? That this number is higher. Now it's 855 million. It used to be 700 and something. It makes sense because we are making the most of that slope. So let's compare this. The first option was 700. The second option is 800. So we have gained energy. So this solution is more efficient than the flat roof. It makes sense. But now, what is the optimum angle? Okay, let's find out. We're going to run different analyses with 40, 50, and 60 degrees. It's not degrees, it's the slope. Okay. So let's go back to the 3D view, and we're going to change the slope. It's 3/12. Now let's say that it's 6/12. Is this better? Let's find out. Solar analysis, you see that sometimes it makes something weird. User selection. I want to select this roof, finish, and it's BTU, solar analysis, update. Okay, it's even better than the other one. But you have to look at the BTU per square feet. Okay, so this is relevant because the areas are different. This surface or this area is different than this, and it's different than that. So it's not just, we don't have to look just at this number. We have to look at the area. Here we have 1,900. Here we have 1,981. And here we have 2,000. So yeah, this number is getting higher, but the roof area is getting higher as well. So we have to look at this BTU per feet square. So in this case, what's 377. This is 432, and this is 461. Okay, so it's not just this number because the area is different. We need to look at the BTU per feet square. Okay, so this is the lowest, and this is the highest number. Let's change the tilt again, and let's make it 9/12. Okay, it's not just the efficiency, it's just the aesthetics. Do you like this? Well, I'm not judging the quality of the project, but of course we have some limitations from the design point of view. We cannot do whatever we feel like, but we're analyzing the energy now. So with the solar analysis, I'm going to select this, finish, cumulative insulation, solar analysis, update. Okay, so if we do this, now we can select and compare. So this is the highest number, I think. It was 992. This is 1,000. But what about the BTU per square feet? This is 46, and this is 47. Well, it's 461 and 471. So even if we look at the BTU per square feet, this is the best option. Okay, so let's do something radical, and let's create a slope with 11 out of 12. Does it work 12 out of 12? By the way, 12 by 12, it's a 45-degree angle. Okay, so that means that we go 12 in horizontal and 12 in vertical. So the angle is 45. I think we can make it higher. Check. Yeah. Okay. So let's do this, something crazy. It's 16. So we have 12 in horizontal, 16 in vertical. So this is around 60 degrees. Okay, so let's try this, the solar analysis. We select all that, we finish, and cumulative update. Well, yeah, does it make any sense? Well, I don't know if we can trust this option. Probably it makes sense because it's almost vertical. So when we are in a vertical or in a, there are some times in the year in which we don't have solar installation or solar irradiance on the, let's pretend that we are trusting Revit on this. And we will compare that. Okay, here probably this number is the highest. It's 1,400,000. That was 1,100,000 because this is the largest area. But if we look at this, if we look at the BTU per square feet, this is 461 and this was 471. Okay, so there's a limit. Probably this is the optimum angle. And if we continue to make the slope higher, well, it doesn't work as well. So the horizontal is the worst orientation. We are getting better until we reach an angle and then we start decreasing the efficiency of the system. Okay, so with this analysis, we can find what the best angle is. We know that it's around 40 degrees or, yeah, so that's the optimum angle in this latitude. Well, we can say that the optimum angle equals latitude. Okay. So what is the latitude? Boston. I'm going to write this in English so that you can understand. Okay, so the latitude is 42. Okay. So the optimum angle would be around 40, 45, something between 40 and 45 would be the optimum angle if we are working in Boston, what is the angles? Degree. How can we convert this? Okay, so this is 4 by 12. If the base is 12 and this is 4. So I want this angle. Okay, so this is 18. If I'm using, what was the optimum? Well, something that we have to write down is the optimum angle here. I think it was 6 and 12. I'll be around 26. Hmm. Or was it 9 by 12? Yes, I think it was 9 by 12, and that was 36. So let's try to find 42. Let's make it 10. And this angle is 39. Let's make it 11. And this angle, okay. 11, I think would be the optimal one. The optimal one. So let's go back to the 3D view. And let's change this 11 by 12. Now we go to the solar analysis. We select this, finish, update. Yep. So look at this. And make sure that you write down the angle. The angle here is 11. 12 is 42. Is it 42? 42.5. 0.5. Okay, so here, this is not the largest number because this is 1,200,000 and this was 1,400,000. But if we look at the BTU per square feet, it's 47 and this was 46 and this was okay, this is 472 and this is 471. Yeah, it's almost the same. Okay, so there's a moment in which well, the slope matters, that from 40 to 42, 43, it's almost the same. But there's a huge difference between this one or the horizontal one and the optimum. Okay, so this is 377, and this is 472. It doesn't mean that you all your roofs have to be like this. No, it doesn't mean that your roofs need to have the optimum slope. But if you don't, okay, what is the slope of my building? I really don't mind. Okay, if it doesn't mind because of the design concept, so you know that the optimum is related to the latitude. So you need to know where you are, and then you need to know the latitude, and then you need to find an angle that it's close to this. Don't go crazy. It's not 42.3601. No, it's 40, it's enough. 44, it would be enough. 45 would be good. Okay, because there's a point in which it doesn't make a difference, 1 degree above or below that optimum. Okay, but this is something very useful, and we can use Revit very easily just to find out this. What is the angle? What is the optimum angle? You have a client. Okay, I have this roof. What is the, or I'm thinking of refurbishing this roof, and I will change the slope. What should I do? Because I want to place PV panels on the roof. Okay, so you can run this analysis very easily, and then you have an idea of if what you are doing is, it's not good or bad. Everything is good. I mean, this is good. So we have this solar yield. It's good, but well, this is better. Yeah, but what if I don't want a tilted roof? Okay, go this way. It doesn't matter. There are more options, especially if you don't want to have a tilted roof. Can you place PV panels horizontally? Well, you can do that. But what if I want to place the optimum angle on a flat roof? Okay, let's do this now. We are just a footprint, and I don't want slope here. And now we have a flat roof. But we want a flat roof, and we want to put a PV array on this roof. How can we do that? Good question. Why is level 1 not showing? Okay, we have these grid lines. This is A, B, C, and what about the north? Okay, we have 1, 2, 3, 4, 5. So let's work with the east elevation, and I'm going to create a roof, architecture roof by extrusion, and I need to set the plane on, what is that level? It's level 12. Okay. Roof by extrusion, it's level 12. But now I want to set this on grid 1. And now I can draw a line. So let's make it 45. Okay. It's 45 degrees, and the length it's 6 feet. 6 is how much? 2 meters. Yeah. So usually these PV panels. Okay. Usually these PV panels are 6 by 3. Usually it can be 5 inches, 5 feet, and 4 inches by 0.8. I don't know, but usually they are 6 by 3 inches. So let's do this. And now we can create, oh, yeah. well, we have this roof by default. We need to change this to something very thin. Okay, so if you don't have it, create a basic roof. It can be even thinner. We can edit type. We can duplicate it. And well, this is 2 inches. Let's make it 1 inch. Okay, we want something that is a roof, but it's something very thin. Are there PV panels here? Yes, there are, but we're not doing that yet. Okay, so we're not inserting a family of PV panels. We're just creating a roof, and the angle is 45. And well, we just need a surface in which we can cast the the sun, or we can hit the sun. Here on this 3D view, yeah, this is what we have. And now the most important decision now is the distance between 2 different PV arrays. So let's copy from this point to that point. Okay, I know that this is not going to work, but I want to realize why it is not working. Okay, so here we have the PV array. We have 2 rows of PV panels, and now we have to find what the total solar irradiance on this panel, on these panels is. So let's do the solar analysis again. I want to analyze solar, and I'm going to use this. But now I want to select. Be careful, because you can select this. You're not selecting the roof. You're just selecting, well, you're not selecting the right surface. You're selecting this, but I want to select this one. And I want to select that one. Okay. So make sure that this is the same cumulative insulation, solar analysis default, finish, and we update. Okay, as you can see, we don't have any sun there. And this is relevant because if half the panel is not receiving any sun, the panel is not working at all. It's not that, okay, so this panel is working at 50% of its ability. No, it's not working at all, because the solar cells detail. Let me. Yeah. So PV panels are made of solar cells. If you connect different solar cells, you have a panel, and if you have different panels, you have a solar array. And those solar cells, they are made of silicon. It's quite difficult because it has to be very pure. So that's why it used to be expensive, but now prices have dropped because of our friends in China, because they are dropping the prices of everything, including PV panels. But what I wanted to show you is, okay, so it's not that simple. So it's not something that we can do at home. Just by having silicon. Oh, I have silicon, so I can manufacture a PV panel. No, it's not that simple, because you have the cell, then you have to encapsulants. So it's like a plastic that protects the PV cell, and then you have a glass, and then you need an aluminum frame. So there are a lot of components, and then you have a junction box, and then you have to connect everything. If you see that cell, you see that there are like 2 cables on that cell. I would like to see a detail. Okay, so you see that we have two, this is the cell with this shape, and here we have two lines. So this line, it's a conductor material, a metal, that connects different cells. If by any chance one of the cells it's half in shape, it doesn't produce any electricity. So it produces electricity, but it's not able to conduct this electricity until the end, because at the end of this line, there's something, and this is what they call here the junction box. Okay, so eventually all these elements are connected to this junction box. If there's a shade somewhere, the flow of electricity is stopped and it doesn't produce any electricity. Okay, so that's why those PV panels are very sensitive, and we cannot pretend that, okay, so we have a shade here, so only half the panel is working. No, the panel is not working at all. If we have more than 20% of shade on this panel, the panel is not working, or we can assume that it's not working. So that's why doing this, it's useless. This second line is not working at all. Okay, and we have to be aware of that. If we have this kind, if almost half the panel is in shade, because here we have 0, or well, it's not 0, but so we can assume that this second line is not working, or this second array is not working at all. So that's why we need this, because with Revit, we can find out that this is happening. How can we prevent this? I can go back to the 3D view. I can go to the right and I can move it. How much? Well, I don't know. Let's move it here. And analyze this again. So we have to select again this. I have already selected these two. Finish and update. Okay. Even this option is not the right one. So I wouldn't do this. I would work, or I would increase the distance. And then with the soil analysis, I select, finish, update. Well, it's getting better. But yeah, we can analyze this in a different way. So imagine that we have the building, we have the sun path on, and we cast shadows. Well, it's impossible. So look at this. At this time, at 7 a.m. On December, or I don't know what day is this. I think this is today. It's March. It's April, whatever. At 7 a.m. we don't have any. Let me work with sun settings, and now we're going to use steel. Okay, so this is today, April the 7th at 9:45 a.m. We apply. Okay, so now it's working well because we have no intersections between these. If we change the time, okay, it works well. There you go. What happens if we change the day let's say December the 21st is always the most critical time of the day of the year. Okay, so on December the 21st at 4 p.m. Probably we won't be having any yield in this second array. Can we move up? Okay, but look at this. Yeah, so look at this. It's almost, this is what I would do. So the worst day, well, it's not the worst condition, but at noon on December the 21st, I would like to have sun in the panel. So I have to move this a little farther. More. Okay. So that would be the perfect distance between these two panels. If we move on, yeah, we have some shade here. It's impossible having, okay, but at least if you create that on December the 21st at noon, we don't have any shade, that will work well. What's the problem with this? The problem with this is, yeah, we don't have a lot of area, because if we place a third array, if we move this from this point to that point, we copy. Okay, that would be the optimum distance, the optimum design of this PV array. We have the optimum angle, and we have the optimum distance between two lanes. So if we analyze the yield of this solar user selection, if we include this one and finish and update. Okay, as you can see, this one is not interrupted, so we have this one is the best. And here, yeah, we have shadows, because on December 21st at 4 p.m. we don't have any sun on these two arrays. But that would be the optimum yield. So I'm going to take a screenshot of this. And I'm going to place it here. And here, the total number is relevant. Okay, so here we have 504. What if we have exactly the same area, but this distance is different? I want to move it here, and I want to move it there. Okay, we have exactly the same area. We haven't changed the area. We have just changed the position of the panels. So I'm going to create the solar analysis again with this, finish, update. Okay, so this is 472. This is 472, and this is 504. And I think this is too optimistic. Okay, so probably this is the the amount of solar radiation that we are receiving, but it doesn't mean that this is the actual electricity that we are generating. We are generating less electricity because sometimes there will be more than 50% of shade on this PV array here. Okay, but here we can compare things. And now, what if we compare this to the optimum? That was the optimum. So that was the angle was 42. So here the angle is 45. The thing is that here we have a lot of area. Here we have 2,600 square feet. And here we only have 1,000 square feet. Okay, so the total number, this is much higher than this. But, well, what if our building doesn't have a tilted roof and we have a flat roof? Then we need to go for this option. Okay. Is it easy? Well, if you have done this thousands of times, you know what the best solution is. So you don't have to, okay, what is the latitude? 42. Okay, that's, what is the optimum angle? Around 40. Let's do that. So you don't have to think about it. Then the distance. I would always use this Revit to analyze the sun or the shadow analysis. I would use the sun settings, still. And I would analyze always December the 21st at noon. And if almost 50% of this panel is in shade, I wouldn't do that. Because at this point, this panel is not producing any electricity because it's half in shade. Okay? So it's a waste of money doing this. Well, I think this is a nice tool, and with little effort, we can have good conclusions. So what would I do? Definitely, I wouldn't do this. If I go for a PV array, that would be the optimum distance and the optimum angle. And well, is this the optimum? I can have flat panels like this. Okay, so here we are producing 726, and with this option, we are producing 505. So having a horizontal surface, because here we don't have shadows, so we're not casting shadows from one panel to the next one. So is this option better than this? Well, what do you think, Zach?
Yeah.
Yeah, what? Which one? This is option 1, and this is option 2. What would you do?
I probably do option 1.
Option 1. What?
Getting more solar.
Yes, that's true. We have more solar BTU. Yeah, so this is 726, and this is 500. The area here is 1,000, and the area there it's almost 2,000. What about the money? Are you going to pay for this, or who's going to pay for the materials? Oh, I hope not. I'm the architect. You are the client. But I show you these two options, and you decide.
I would choose that. I would choose that one because I get more sun, because the other one you're getting shade on the back half, so you're using.
Yeah, in terms, I know it's not an easy question. The thing is, okay, this is what I received, 500, and with this option, I received 700. But now money is an issue. because okay, yeah, so this option is better because I'm receiving more sun, so I would do this. Okay, what about money? And I don't like to think about money in this kind of courses, but how much does it cost? A solar panel, a PV panel. Do you have any idea?
$400.
$400.
Well, a couple hundred. I mean, maybe
A couple. $1,000.
I would guess like 300.
Okay, so let's make.
Not bad.
You say 300.
Yeah.
We are talking about something which is around 6 feet by 3.
Let me get $301.
299.
Let's say 300. Zach?
I'm saying probably around 500.
I'll split them in half. I'll say 4.
4.
Yeah.
Well, it's not a huge difference. One might say 2,000. One might say 20. No, but you think that it's around 300, 400, 500. Well, it depends. Let's find out. In my favorite website ever, which is Alibaba. Yes. Alibaba PV panel. $7. I told you, Chinese people have changed the face of the earth. Well, there are others which are 950.
I think that's $10 one.
This is 10 pieces.
Yeah.
Okay, so it's like 95. Okay, so prices have dropped a lot. And we need to see this because this panel is a 300 watt, one piece. This is a 375 watt, one piece. So this is more expensive because it's better. And this is 335. But this was true. Well, I'd say if we were in 2000, I mean, the price of PV panels was around $1,000. The price dropped. I think this would be 2010. If we're in 2021, it's around $7.
Do you know why the price went
They are massively producing PV panels in China. In 2000, there were a couple of factories, one in Germany and the other one in the United States. Now, Alibaba is delivering PV panels, like they deliver pizzas. Okay. Yeah, so things have changed. Now it makes sense. Back in 2000, I remember that when I started studying this back in 2000, I attended a conference of experts and they claimed the PV panel is dead. So this technology is obsolete. We are not using PV panels anymore. And in the near future, nobody will use PV panels. That was in 2000. And it made sense because is it worth paying $1,000 for a PV panel that produces 300 watts? No, it's not. But now, instead of $1,000, it's 16 or 17. No, 60 or 70. Things have changed. Does it mean that the technology is much better now? No, not really. There are, and we have to, because now we are talking about money, and well, if you are thinking of 10 PV panels, 10 times 60, it's $600. I mean, there's not a big difference between $600 or $700 upfront. I mean, but if you are thinking of a huge building, imagine like this. What is the size of the PV array that we have in this building?
It's the size of an Olympic ice rink.
It's. I mean, I don't know how many panels we have here, but we are talking about thousands of dollars because there might be hundreds of panels. Okay, so if there are 200 panels times $100, yeah, we are talking about 100,000 upfront payment for this PV array. So it's a lot of money. And if you are doing this, you are looking for the best yield. And this is what we have to look. So the second option, well, the first option is to look at the money. I think we can afford this in our single family house. Then the second thing that we have to look at is the yield. So the watt per piece or the watt per square feet. Okay, so we need to look at this. But probably if we open this catalog, we will have, well, I wouldn't buy this without looking at these specifications. And if we go to the source, it's monocrystalline silicone. Do we have, it's ready to ship. Um, 370 watts. Okay, so here we have quick details. It's manufactured in China. Here we have the size. Okay, the size, it's around, it's always in meters. So it's 2 meters by 1 meter. It's around 6 by 3. Yeah, so this is the, but I want to see the panel efficiency. That's important. It's 19.1%. It's quite good. Usually those efficiencies are always below 20%. But everything that is above 15, it's good. So this 19% is quite good. And I would like to see the watts. Okay, so this is it. We have the maximum power. Here we have different options, different models. Okay, from 365 to 385. Yeah, that makes sense. And we have a warranty. Yeah, this warranty is always 25 years. So that is something important. So they warranty the panel for 25 years. You won't find something better than this. So I think 25 years is the limit for the warranty. And the junction box, right? Well, I trust this company. Definitely, I would go for it. Okay, because I have a lot of information here. We have a good warranty. What else do we need? And the price is, yep. These prices are per watt. Yeah, it's a little tricky. But what is the price of
Is that up on the upper right there? Is that it?
Oh yeah, so 190. But this is low price solar panel, monocrystalline, 100. But is it just one piece or? Well, this is shipped to the United States. Probably, yeah, we have the price here, and then that includes shipment, which is always. Anyway, prices have dropped dramatically. And now it's a question of looking at the technical specifications. It's looking at the warranty, it's important. It's the power, the maximum power that we can produce, that is important. And the price is not only, because usually in this price, the junction box and all the things that you need, the inverter and all that stuff, it's included. I need to find out more. but they have a lot of certificates. And they have even this one. There was an issue with this CE, because this is the CE brand. The CE marking, it's something that the European Union certifies. Okay, so this is the European Economic Area. So if you see this symbol, that means that is certified by the European Union, and this is something very serious. But there's another brand which is Chinese export, which is almost the same. Okay. Okay, this is the logo, and this is the Chinese export logo. Can you tell the difference? I don't know. Anyway, there was an issue with the, well, that's a long story. But doing this, I mean, it's a question that first you need to understand that you need an investment. The investment now is affordable. It's something that a family can afford now for a single family house. Back in 2000, 20 years ago, it was impossible because it was too expensive to use PV panels in single family houses. Now it's something affordable, and why not? People are thinking about this. And again, it's something about relying on the company. You can buy your PV panels from Alibaba. They ship your panels. And if you are a do-it-yourself person, you can go up to your roof and you can install this. It's not difficult. Okay. Or you can rely on a company. No, we have done this in the key area. So there are hundreds of thousands of houses with our technology, and you know, oh, your neighbor has this, or are you happy with this? Yes, I'm saving a lot of money. Okay, it's a question of relying on this. So we have the calculations, and then we have the deployment of the PV array, and this is even more important than the calculation itself. But it's a job opportunity now. I mean, there's a demand for this kind of energy because it's efficient and it's cheap. It's affordable. It's not cheap. It's something that everybody can afford. And now, and with a little knowledge, I think you can get a good job with these kind of things. That you need to contact people installing this because calculations are not enough. You need someone to install and someone you can rely on, and someone who is responsible for, because we have a warranty for the panel itself, but then we need a warranty for the installation itself because all the connections have to be good. But the market is growing. I don't know if I showed you not Alibaba. Okay. Okay, there you go. This is my brother's house. And I don't know if I had to rate people in terms of their concern about the sustainability and global warming issues, my brother is at the bottom of the list. And he has PV panels. Why? Because it works, because he's saving a lot of money with this. And in this neighborhood, well, it's good because he has this south-oriented roof. So this is Google Maps. So this is facing south. He has this slope. We have a chimney here. And yeah, so we have to avoid this chimney. And look at the trees. I'm sure that they had this study and they placed the panels where they didn't have enough or they didn't have shadows from the trees. This is something that we have to analyze. It's not just the shadow that some panels is casting on each other, but what we have surrounding the building, surrounding the house. And he did it because it's a good business. And as you can see in this neighborhood, it catches the eye that there are a lot of people with this PV arrays. Well, it's not massive yet, but there are people doing this. So here we have more. Okay. But look at how many roofs we have here. So first we have to analyze the potential of these houses to have PV panels on it. And then you can go door by door. Okay, so do you know your neighbor? Do you know that your neighbor is saving $100 per month with his PV array? No kidding. Yeah. Well, it's an option because with this kind of construction, look at this. All these houses are south oriented, and they have a nice part of the roof here. So all of them could have like the panels that they need to provide energy for themselves for free. Okay. Okay. So how much money do I have to pay up front? I don't know, $1,000. And what is the return of investment? Well, some people are doing it because you see that, yeah, probably 1 out of 10 houses now they have this. But what if 9 out of 10 houses had PV panels? Probably it would be different. Okay. Let's think about it for a design option, but even for your future business option. I think now everything is booming, prices are dropping. As you can see, not everybody has done it yet. So there's a room for a job here, just installing PV panels on every single roof. It has to be, yeah, you have to offer the whole 9 yards. I mean, the energy retrofit, because installing PV panels on a house that it's not efficient, it doesn't make any sense because, yeah, you are spending some money on something that the first thing that you have to do is to save money with the envelope of the building. But if you are, I mean, now with these prices of PV panels, there's an option to make your clients happy, saving the planet, and earning some money. So it's a good option. Okay, let's get back to Revit. What can we do now? So we have analyzed different options in terms of the slope. Then we have analyzed different options in terms of the distance between these two panels. And now you know the price. So now you know the price of 1,900 square feet, and you know the price of 1,000 square feet. And you know the difference between the energy that you can generate. And now it's a question, we need to know the price of the energy. Yeah, so that's another issue. price of electricity in do I have to log in? No way. Okay, that's interesting. We have commercial electricity rates and residential electricity rates. They are different. And in commercial buildings, everything is cheaper. Why? Because of the amount of energy that they are using. But in residential buildings, it's around 16 cents per kilowatt hour. Again, is this too much? It depends. How many kilowatt hours are you consuming? By this time, you should be able to know that. Zach, what is your cooling load? The peak cooling load?
Was my cooling load?
Yes.
It was. So my cooling load was.
Only before.
So my cooling load was 98,135.
19,000 units.
BTU hours.
BTU hour. Okay, in electricity, I told you that we are not using BTUs, we are using kilowatt hours, and when we are looking at the prices of electricity, it's always in kilowatt hours. Okay, so we have to turn this into kilowatt hours. So we need, this is the data that we need, this is the price. Okay, so first, we need to know the cooling load. Then we have to turn this into kilowatts because, yeah, we have to do it. So we can convert this BTU hour to kilowatt conversion. So it was 92,000, 98,000. Convert. Okay, so this is around 28.7 kilowatts. 28.7 kilowatts. Okay, now this is the cooling load in kilowatts. Now we have to turn this, cooling load is power. Now we have to turn this into energy. So we need to multiply, we need to turn kilowatts into kilowatt hours. So we need to multiply times hours. How many hours? Let's do it on a monthly basis. What is the schedule of the building? Let's say that we are using the building 10 hours per day times 30 days. So in total, we have 300 hours per month. So what is the total energy?
8,610.
8, sorry?
8,610.
610.
Yeah.
Kilowatt hour. If this is the energy price, so what is the total electricity bill?
$140,256.90.
140?
140,256.90.
140,000.
Yeah.
This is cents, it's not dollars. So it should be 1,400.
1,400.
Okay, that makes sense. Okay, 1,400. So this is not a single family house, it's an office building. So it would be more of a commercial building. So if it's a commercial building, now the price is not 16, it's 9.56. Okay, let's do this. Zach, can you do this with 9.56?
8,231.
8,000?
Yeah.
8,000 or 800?
Probably 800. I'm doing my math now.
I think it would be 800. It's not that I don't trust you, but let me
I'm not trusting myself.
make sure, very sure. So this is 8, 6, 1, 10 times 9.56 divided by 100. Yeah, 823. So now we are talking about dollars. Okay, so this is the price. Why do we have, well, that makes sense. The more electricity you use, the cheaper the electricity is. So in a commercial building, you use more electricity than in a single family house. So they charge you more in single family houses. Okay, but anyway, if it's a single family house, we will be talking about 1,400. If this is a commercial building, we will be talking about 800. But this is the total electricity bill. We need to know that because now if we are using, let's say 2,000, now the option is the PV array. Array, and then we have option 1. And in option 1, there is this area, it's around 2,000 square feet. 2,000 square feet. And option 2, it's around 1,000 square feet, which is this one. Okay, so this is around 1,000 square feet. This one is around 2,000. Now, what is the price of the PV array? Let's say $100. $100 is around, yeah, because this is 6 by 3. Okay. It's 18 square feet. So it's $100. Divided by 18 square feet. So what is the total price of option 1?
$11,111.
11,100. Kind of. And what is the price of option 2? It should be half, like
75.
5,555.
5,500 around. Okay, so this is the money that your client has to pay upfront. 11,000 or 5,000? So this is the money that we are, and now there's a third option that we don't know yet, and we will find out not today, but later. What is the yield of this PV array? Because this is the money that we need to pay up front, okay? And this is my electricity bill. I need to know the production, so we can do this with Revit. I think we can, but let's go back to this option. Yep, so that was the option that we are analyzing. And we need to run a solar analysis. Solar, user selection. I'm analyzing this, but now instead of this custom finish, I'm going to use the solar energy, the annual solar energy. And we have the cumulative insulation. No, I want the PV energy. And style solar analysis, annual PV energy. Okay, so now we are analyzing the energy that we are producing, not the energy that it's heating on our panels. It's the energy that our panel is producing. So let's update and see what happens. Okay, and we are producing 23,600 kilowatt hour per year. Okay, so if this is option 2, we are producing 23,600 kilowatt hour per year. This is kilowatt hour per month. Let's say that we are working with 12 months. How much is this?
103,320.
100?
103,000.
103,000 kilowatt hour per year. Okay. So if we are producing 23 over 1,000. So now the consumption is this, and production is that. Okay, so basically this is for free, like 1/4 of the energy that we are consuming. This is for option 2. What about for option 1? In option 1, we have this, but we can find out the amount of energy that we are producing. So I'm deleting these panels and I'm running the solar analysis here, that now I want to analyze this. Finish. And I want to analyze the annual PV, cumulative insulation, and the annual PV energy. Update. Okay, so we are producing 34,000. The production is 34,000. The consumption is the same. Now, what are my savings? It's 103,000 minus 34,000, which is 69,000 kilowatt hours. And what are my savings here? The consumption is the same and the production is 23,600. And this is 79,400. Okay, so this is what the client needs. You are saving this. Let's make it smaller. What's the price of energy? Dollars. Let's use for the commercial building. How much is this? 69,000 times 3 cents, 9.56 cents. 69 times 9.56 divided by 100, 6,000. About 6,596. 6,596 dollars. Here. And what about this one?
The other one is 7590.64.
7,590.
Yeah.
Okay.
They're saving $1,000 more.
Yeah, so I'm saving $7,000, around $7,000 per year. And I'm paying upfront 11,000 and 5,000. So look at this. In this option 2, the first year, I have recovered the investment. And here it takes like 2 years. This is too optimistic. Okay, so I think either the price of PV panels, I don't know. But this is a calculation. It might be wrong, but this is what the client needs to know. Usually this is around 5-6 years, so that would be more feasible. This is too optimistic. I mean, this option 2 would be oh no. No. Okay, I've done this. No. These are not the savings. I'm producing this. So this is my current bill. Okay, so this is what I will be. This is not the saving. This is what I will be end up paying. So I'm saving 34. Yeah, so let's do this. Sorry. So the savings is the production, and here, yeah. So what is this again? 34 times this. 34,000 times 9.56 divided by 100. 3,000. Okay, so 3,000 to 250. And with this one, this is 23,600. Okay, because this is the production, 23,600 kilowatt hours per year times this.
2256.
22. Let me do it. Yeah, 22. 2, 2, 5, 6. Yeah, so with this, it takes, it's even too optimistic. It takes 2 to 3 years to recover the investment. And with this one, it takes, yeah, like 4 years to recover the upfront money that we have paid.
How long, when you build like a solar array, how long can you expect it to last? Like 30 years, 25 years?
25.
25?
The warranty, I mean, 25 is worldwide. It's not only in Alibaba. So in 25 years, it's worldwide. But that means that after 25 years, most likely it won't be producing anything. And there's another issue with this. This is because we haven't taken any heat loss from this production. If it gets dirt, I mean, if the dust, the snow, that affects the production of the PV panel, and Revit hasn't taken that into account. So maintenance is important. So you need to add here maintenance. So every year or twice a year, someone has to go up, and then they have to clean up all the PV, and it takes that.
Is there like a natural like degradation to how much electricity it produces every year too?
Sure. I think we saw something like that on the I have closed the Alibaba. Yep. I think there was like a curve. There was like a curve. So there's a drop in the production. This is the optimum at the beginning of the life panel, and this is what they guarantee at the end of the life cycle. And here we have a curve like this. So in 13 years, we expect to lose this percentage of production. Yeah, so we have to refine this, and that's why we're going to use another software, but with the big numbers. If we have this, we can say, okay, in a couple of years, according to this, or 3 years, you recover the initial investment. Okay, this is too optimistic, but if it's in these calculations, we have 3 years, well, most likely it will be 5 or 6, and it's good. If it's less than 10, people will go for it. But you have to be very sure of this curve, because you need to sign a contract with your client. And what if your expectations are too high, and at the end, after 10 years, they tell you, okay, I haven't recovered my investment. Then you go to the trial. Is it because of lack of maintenance? Well, I told you in this contract, you see that twice a year, you have to go and clean up have you done this? No, I haven't. Okay, so you haven't done this, you can't expect to have the full production. But those are the numbers, and yeah, we need to add the money. We're not doing this in this course, okay? So we're just looking at the best option in terms of angles, in terms of energy production, in terms of the slope, the distance between panels. This is what we are looking for. But eventually, you will need to, and why are we doing this? Because this price, we cannot control this price. Maybe now it's 9.56 cents, but maybe in the near future is 20 or 5, we don't know. So that's, but this, the kilowatt hours, it's something that we can control. If, well, we can control, we depend on the PV panel. But if we have this certificate, we have to trust on the certificate of, or the specifications of this PV panel. We have to trust that. If we don't, but this price, and you see that it's different. This is a commercial building. This is a residential building, and prices are different. And in every single state, the price of electricity is different. This is in New Hampshire, or even in different cities, even the prices are different. So we can't control this price, but we can control the slope, the distance, because this is architecture. So controlling the angles, distance between panels, that's something that is in our job. The price of electricity, who knows?